Prynhawn da a croeso. Good afternoon and a very warm welcome to you all. Thank you for joining the first of 3 sessions today which celebrate women working in science and technology, which is part of the Wales MIT Virtual Conference Series. As many of you will know, MIT is one of the world's largest academic and research institutions with globally renowned expertise in areas such as science, leadership, technology and engineering. It also boasts 93 Nobel accolades amongst many other laureates. Research has shown that the MIT alumni have launched over 30,000 companies around the world, employing over 4 million people and generating almost $2 trillion in annual revenue. As you might expect, many global businesses seek to partner with MIT, including familiar names such as Google, Shell, Intel, Siemens, and Samsung. But businesses here in Wales are also able to engage directly with the MIT through the Welsh Government membership of the Industrial Liaison Programme, which has made today's session possible. This includes access to the latest online resources and research, webinars, and bespoke meetings with the MIT faculty for specific areas of interest. My name is Rachel Gapansky, and I am a project coordinator at the AMRC Cymru, and I am delighted to be your host for today's session. The Advanced Manufacturing Research Centre was established 20 years ago in Sheffield, England, and is a world leader in manufacturing materials and machining research. We focus on academic learning, industrial commercialisation, and making step changes in productivity, increasing competitiveness, developing new products and processes, and training new talent and skills. The scope and organisation of the AMRC has grown significantly since we were founded in 2001, and we have built up a portfolio of over 125 industrial partners. These are ranging from globally engineering giants such as Airbus, Boeing, and Rolls-Royce through to smaller companies. Businesses can work with us on a one-off project or join the AMRC as a member for long-term collaboration. In order to better support the Welsh manufacturing system, the state-of-the-art AMRC Cymru was opened in November 2019 with a focus on advanced manufacturing in the aerospace, automation, food and drink, and nuclear sectors. During the coronavirus pandemic, the AMRC Cymru workshop was completely transformed in less than 2 weeks to support the manufacturing of the ventilator project. Following on from this, the workshop has been reset and is fully fitted out to support a broad range of new technical challenges and projects. So today, I'm delighted to introduce today's session on decarbonising the construction industry with Caitlin Mueller. Caitlin is a researcher, designer, and educator working in the flagship in architectural and structural engineering. She is also an associate professor where she in the building technology program where she leads the digital structures research group. As a researcher, Caitlin develops new computational methods and tools for synchronizing architectural and structural intentions for early stage design. She also works in the digital field of digital fabrication, where she is linking high structural performance with new methods of architectural makings. In addition to her digital work, she constructs research in the line of collaboration with architects and engineers from a historical perspective. Caitlin also aims for interdisciplinary learning and integration in her teaching efforts, which includes subjects in structural design and computational methods. I hope you're looking forward to today's session as much as me, and if you have any questions, please feel free to use the Q&A function and we will address as many of these as possible at the end of the session. I'll now hand over to Caitlin.
Great, thank you so much, Rachel. All right. So it's a pleasure to be with you this afternoon. As Rachel said, I'm Caitlin Mueller. I'm faculty here at MIT in Architecture and Civil and Environmental Engineering. My talk is called Decarbonising the Construction Sector, and it's based on about 8 years of research that I've done with my group, Digital Structures, which consists of a diverse range of graduate students and undergraduates at MIT with backgrounds in architecture, civil and environmental engineering, mechanical engineering, computer science, and applied mathematics. Our diverse backgrounds are unified by our interest in performance in the built environment in design and construction. And we're motivated by historical and contemporary buildings such as these, which come from around the world, are constructed in a diverse range of materials, look significantly different from each other, but are united in that they all use material in a very intelligent and minimalist way. They're all using material only as it's needed structurally, and that constraint of material minimization is what gives them these incredible geometric forms. There's this amazing potential in the relationship between architectural expression and structural efficiency that I seek to exploit and further develop in my own research. And I show this when I start because sometimes when I talk about high performance design, people worry that I'm interested in a homogenization of the built environment or that all buildings should look the same. And I think it's really the opposite. We can really expand our human potential by using performance as one of the drivers in the design process for the built environment. It's also critical that we do this today. We have an enormous climate imperative to pay more attention to the performance of the built environment. This is an example of two recent stadia built for the Olympics. On the left, the 2008 Olympic Stadium in Beijing. On the right, the London Olympic Stadium from 2012. They're both made out of steel. They're both large stadiums with the same purpose. The Beijing Olympic Stadium on the left uses 14 times the carbon emissions embodied in the materials per seat compared to the London Olympic Stadium. So not 14% more, 14 times more. That's a performance differential that's really unbelievable. In any other sector, we would not see that kind of range. And it's because we haven't been paying enough attention to this for a long time. But today's climate imperative requires that we be more mindful about the emissions associated with buildings and infrastructure, and more particularly with the materials that we use to build them. This is important and challenging. It's challenging to pay more attention to this because as we develop a design process, we usually don't know very much about it until we get to the end of the process. So our concept in the beginning is very open. We have a lot of freedom, we have a lot of potential, but it's very hard for us to understand how our design concept performs almost until it's too late. And in an ideal world, we would use the principles of engineering and the principles of performance simulation as early as possible while conceptualizing a design. But too often, this happens really at the end. We're only using engineering to verify or validate a crystallized design concept rather than to help generate its key features. This is also challenging because of the disciplines that affect the built environment that have a lot in common in terms of their interests, but are very separated and polarized in terms of how they are contemporarily conceived. So for example, the two fields that I work in, architecture and structural engineering, both work on buildings and infrastructure, literally the same objects, and yet the way they approach it are completely different and in many cases completely isolated. So for example, the way computation is engaged is very different in architecture versus engineering. The way that we think about fabrication, construction, materialization is very different. And even the way we think about educating architects and engineers has almost no overlap. So in my work, I'm really interested in finding ways to bring these fields closer together so that we can engage a more integrated and synthetic process to lead to a better built environment. And I think this is not only important in terms of the practical outcomes of using less material and using it more responsibly, but again, I also think this can advance our potential as designers and expand the palette of architectural form. I do a lot of this work through what I call the design space, and this is a computational technique for understanding both sort of what a building looks like or what a design's design characteristics are and performance in a single kind of landscape that maps these two concepts together. So in this example, this is a design space for a really simple structure for a truss that supports a given load. And I can change what this truss looks like by making it shallower or deeper or wider or narrower. And as I make those changes geometrically, it both changes the appearance of the truss and its efficiency. It changes how much material is required to support the load. And what these blue landscapes show is a mapping of that relationship between design and performance. This is the design space. Using methods that have existed for decades, since before I was born, We can find the optimal solution in the design space. Those are here. There's a global optimum and a local optimum. And yet optimization methods, while very powerful, are almost never used in the design of buildings or infrastructure. And I would argue that's because it's really hard for us to fully articulate the goals that we care about in design. We care about performance and minimizing carbon emissions and using less material. But in architecture and in buildings, we also care about a lot of other things that are really hard to mathematically express. And so in my work, I try to balance the interest in performance-driven design with the ability to accommodate additional human considerations that are often really important in the design of buildings, for example. So if we do that here, if we just relax our problem a little bit and look at designs that aren't only optimal, but that are high performing here, these are trusses that perform 10, 20, 30% worse than the absolute optimal design, we have a much more diverse palette that can accommodate a wider range of interests from humans, occupants, the sort of the soft side of design that's so important to consider. In my work, I develop computational methods to try to understand and explore design spaces. This is an early tool that I built to do this called Structure Fit, which designs long span trusses. You can think of them as bridges or roofs. And like the earlier example I showed, by changing the geometry of the structure, you can also change its performance. And what this tool allows you to do is visualize a range of possible options for a truss, understand the numerical performance. Here, a lower number indicates better performance, less material required. It's normalized by the amount of material required by the original idea, so less than 1 means we're improving. And it uses an interactive evolutionary algorithm that allows a human and a computer to collaborate, to explore and evolve designs together, to find designs that meet the preferences that the designer indicates through selection, but that are also moving towards higher performance. So this is an alternative to optimization that I think is more relevant for the design and construction sector, where we're able to balance the criteria that we can express in the computer and those that rely on human expertise and intuition. And what this tool allows us to do is not only discover the very best designs, but also to discover new and surprising designs that are that might meet this balance of criteria. So for example, these are all designed with Structure Fit. The designs on the left are the kind of original ideas that one might have, for example, for a transmission tower, for a roof, for a building frame, for a bridge. And as we move from the left to the right, the designs become more efficient. It's hard to see the numbers, but they're getting smaller and smaller and smaller. All the way on the right are designs that we know from history to be very high performing. These mimic designs that were designed through analytical methods. But what I also find interesting about this range is that there are other designs that are not the solution to any optimization problem, but that might be the most interesting from the perspective of the designer, the occupants, human society, and that are also very high performing. So this is an approach that allows us to balance these goals and make it more relevant for real applications. When we move into more complicated structures, in 3D, for example, we can see the same principles apply, that there are diverse possible solutions that are high performing. And in 3D, there are even more possible load paths. So for example, this is what we call a design space catalog of interesting good solutions. Again, a lower number is better. Again, the number corresponds to material consumption or carbon emissions. And what we see here is that there are so many different ways to express performance visually, and different people or different cultures or different regions might choose to use different designs. All of them are high performing, and all of them are discoverable through these computational methods. We also use techniques such as multi-objective optimization, which is a method that allows you to compare multiple quantitative goals in a design process. This is really important in the design of buildings and infrastructure because almost always we have more than one goal, and often those goals are competing with each other. If we only design for one, we could seriously miss out on the other. So for example, in this design, we're looking at a shell roof structure, kind of a long span, interesting roof, whose shape dictates both its structural efficiency and the amount of energy that is required to condition the space. Traditionally, these two concerns are studied entirely independently by different types of consultants with different backgrounds. There's very little collaboration. This technique, multi-objective optimization, allows us to start to integrate and synthesize these different concerns to find solutions that balance them. What we see here in this curve, this is called the Pareto front. And this shows the designs that represent the best trade-off between the two objectives. And we use this technique widely in a lot of different applications. We're also really interested in how to make the simulation methods that we use to measure performance more relevant and accessible in early stage design when they can have the most impact. And this is in response to many studies on human-computer interaction that have shown that when the computer is too slow, it really disrupts the creative flow, and it's not really useful in an early stage creative process. And many types of simulation, cost estimation, finite element analysis, computational fluid dynamics, the kinds of things that are important, that provide important information for designers, are too slow to be used in their natural state in an interactive, design-friendly way. So we use a technique called surrogate modeling, which is a machine learning technique that replaces these important but slow simulations with a data-driven model that allows us to use this information fluidly and instantaneously in a design process through a predictive model. Here's an example of what that looks like. Here a designer is creating another long span roof with an interesting form. The shape of the structure directly impacts, again, how it behaves, and it also affects, of course, how it looks. Here, the designer is able to work within an interactive design environment, a 3D modeling environment, and instantaneously get the results from a finite element analysis. It's a surrogate model, so it's a prediction, as they change the shape of the design. Here, the color fields represent displacement of the structure in X, Y, and Z, but they could also represent stresses or other relevant information that traditionally takes place in a different software tool that is relatively cumbersome to interact with design frameworks. We can also use this kind of surrogate model to predict even more complex fields of information for a design. Here, we're using a technique called Topology Optimization, which allocates material optimally within a design domain. For example, this is another roof with an interesting rib structure. Topology optimization takes a long time to run and is typically not used in early stage design, but we were able to build a surrogate model where we can predict the optimal distribution of material for a structure under a given load with a machine learning model that works really well across a diverse range of conditions. So each one of these designs is the roof seen from above, and with different geometric properties, there are different optimal material allocations, and our model predicts them almost perfectly and works incredibly quickly. And the outcome of this is that we can then, again, turn this kind of sculpting environment of the designer into an environment that is also an engineering toolbox, where simultaneously we're understanding form and space and architectural concerns, but also getting physics and engineering information about material consumption and performance, and here even understanding what that means in terms of spatial and formal material allocation. This is a process that with traditional tools would take weeks or months and therefore is almost never used in construction today. But in the future, now that we can do this so quickly and in such a fluid and seamless way, this could become kind of standard in an architect's and an engineer's toolbox for early stage design. We're also interested in thinking more generally about where designs come from. How do we come up with design ideas? And even today, with all the advances of computation, design ideas still usually come from kind of our own brains. But what if we could use computers to help us guide us towards designs, not necessarily through optimization, but through a better understanding of the relationship between design variables and geometry and performance? Here we're proposing doing that where we start to build this inverse model between performance and geometry. And we can do that with a range of statistical techniques. Here we're using something called principal component analysis, which is a technique that allows us to find patterns in data. So we do this by simulating large numbers of possible designs. In this case, these are structures, and identifying the directions in the design data that correspond most with the performance metrics that we're interested in. And what we see is kind of a new way to understand the design space. This is a synthetic design space where the computer has pointed us in the right directions. It hasn't told us the solution, but it's helped us create our own little brainstorming tool where we can understand variations of design options and how they correspond with performance. And we can do this in even more complex ways with recent advances in machine learning, in particular with so-called generative modeling or latent modeling, where we can find low-dimensional representations of high-dimensional design data. So for example, a design space that contains tens or hundreds of variables and is really too hard for us to navigate as humans and understand those relationships, we can start to use these machine learning models to build that understanding and to project the high dimensional information down into what we call a low dimensional latent space, governed by performance. And I won't go into a lot of detail about what this does, but it's a way for us to create bespoke visualizations and design spaces of different design alternatives that all perform really well but are significantly different from each other, and allow us to find the relationships between them. So if I like a design over here in the space and my collaborator likes one over here, we can now find the pathway through the design space and start to use that as a way to compromise between these options. And here you can see this roof is morphing and changing in response to the sort of variable projection, but it's also always showing us high-performing designs. And this is a way for us to exploit the fact that the design space almost always has lots of good options. We just need to find where they are. In addition to the work that I do with computational design and trying to make performance-driven design more accessible and relevant to the construction sector, I'm also really interested in the question of construction itself. And one of the things that I found in my own research is that almost always the designs that I'm able to generate on the computer that I claim are really high performing, that can use very little amounts of material, that achieve really high stiffness, are almost always very complex geometrically. And that's because the physics of structural load transfer has a lot to do with the physics of nature. When we look at high-performing structures in nature, they're not rectilinear, right? They're not orthogonal boxes. There are these curving, amazing trajectories of stress through space. And that's what these high-performing structures also look like. But they're very incompatible with 20th century means of construction, where we really prioritize standardization. So how can we overcome that? I would argue it's really important that we overcome that we find ways to economically build high-performance designs, even though they're complex. So how do we deal with this complexity? One possible way forward is through automation in construction, through in architecture what's called digital fabrication or computational fabrication, where we take advantage of the dexterity and programmability of machines and use that to build structures that are indifferent to geometric complexity. This is an example of a technique we built in our lab where we mounted a 3D printing extruder to a 6-axis robotic arm and allowed it to make spatial trusses. And the robot doesn't care if every joint is the same or if every joint is different. It's just as easy for it to make this either way. And it allows us to start to really materialize these structures that we know from our computational work are highly efficient, much more efficient than their standardized alternatives, and to do so in a way that is economically competitive. We also do this for structures who are even more complex in terms of how their interior components are arranged. This is an example, again, using a type of topology optimization where we find the absolute ideal position for every element in the structure. And the absolute ideal position from a structural perspective is not ideal from a traditional construction perspective. But with robotics, we can find ways around this. And we've been working with state-of-the-art techniques in task and motion planning from robotics to automate the process of figuring out what the robot should do. We give the robot a design and we run our algorithm and compute the load path or the tool path for the robot to execute. And what it looks like is something like this, where we can take this is a small model of a topology optimized bridge, but the same principles apply at full scale. And we're able to build it pretty easily with a robot in a fully automated way. This is a design that if I were personally trying to build this myself with my hands, I would struggle with immensely. And yet for the robot, this is no problem at all. And what our algorithm does to work with the robot, it not only considers how to build the structure, it finds the optimal sequence, or it finds a high-performing sequence for the structure to be constructed so that the robot doesn't collide with the structure under construction or itself. And it also makes sure that the structure is stiff enough during its partially assembled state for it to be completed. So we can add all of these different constraints into the task and motion planning platform, and even have multiple robots collaborate together to create complex structures. So this is an extension of that work where 3 robots are working together to assemble an efficient but complex structure. The idea is not necessarily to fully automate construction. We would, for example, still have a human come and assist with the welds between these elements. But what the robotics allows us to do is to be very precise with precision and to remove a lot of the challenge of assembling something irregular or non-standard that's driven by material efficiency. We also apply the same kinds of thinking and techniques to more practical problems that are of urgency and impact today. One area that we've done a lot of work in is looking at reinforced concrete construction, especially in the global south, where we're seeing immense amount of urbanization and need for housing and construction more generally. What we see in this part of the world, and really in most parts of the world today in concrete construction, is a lot of material that's not necessary structurally, but is there in order to make construction easier. So for example, large flat concrete slabs that span between beams or span directly to columns. We know that that's not the most efficient way for us to support loads, and yet we typically do it because we have the sense that it's much easier for us to build something this way and therefore much cheaper. But the opportunity, if we reconsider this, is enormous. If we carve away the material that we don't need structurally and find a way to build these types of structures economically, we can save 60, 70, up to 80% of the material, of the embodied carbon and the embodied energy in these systems. And in many parts of the world, material costs also dominate total construction costs. Of course, in the United States, that's not true. Construction costs are dominated by labor. But for example, in India, where we've done a lot of work, construction costs are about 70% due to material quantities. So if we can reduce materials, we can also make construction more affordable. So we think it's worth figuring out how to do this, even if it means a change to the status quo. Here are examples of the types of floor systems that we've designed with our tools. And what we propose is not a single design solution, but really a platform of alternative solutions that can be tuned to different fabrication techniques or available manufacturing expertise in different regions in the world. And what we can see in general is moving away from a flat slab results in a serious reduction in mass, and EE means embodied energy. And there are different degrees to which we can push this depending on fabrication. This is an example of our tool, which optimizes reinforced concrete floor systems using a constrained optimization approach. What's special about our tool is that it doesn't use anything special in terms of material or engineering mechanics. It's based on today's building codes and today's widely available construction materials. Everything that's special comes from the geometry or the shape. And we can also ensure that the shapes that we are generating are fabricatable by parametrizing the structure in such a way that it meets mold making techniques, for example. Here's an example of a prototype that we built with partners outside of Delhi. And we originally thought we would build this by using a 3-axis CNC mill to mill away some kind of formwork like a foam-based formwork like EPS. It turned out that EPS wasn't available in India in those quantities because it's so environmentally destructive. So originally our collaborators proposed using a solid block of steel that we would mill down. But we all agreed that would be very wasteful in terms of materials. And it turned out that they had a lot of expertise making formwork out of singly curved, laser cut steel sheets that they spot welded together. This was how they built many types of formwork already. So we reparameterized our model using that technique, and we were able to build a structure that was still very high performing and that met their current fabrication expertise. They built this steel form that could be reused 50 to 100 times and resulted in about 50% or 60% less embodied energy compared to a flat equivalent slab. We see this as something with a lot of potential as well in terms of architecture, where these beautiful shaped slabs can also start to play a role in how we think about interior spaces. In terms of how we think about energy and cooling, these slabs can also take on a thermal role. So we're continuing to explore concrete as a construction material and thinking about what its future can look like in order to reduce its environmental impact and increase its functionality and beauty in housing and buildings in general. And then this final project that I'll show is a little bit more speculative, that also thinks about fabrication and construction, but thinks about alternative supply chains. In a lot of our current construction practices around the world, we operate with an assumption of infinite material supply. And we've seen in the recent years that that's a pretty brittle assumption, right? Global supply chains are really are not infinite and can easily be broken by far-flung events. In this project, we ask, what if instead we look at much more limited and constrained supply chains based on locally available resources? In this project, we worked with tree forks that were collected from around the MIT area, initially from a nearby city called Somerville, where they were taking down a lot of trees for the construction of a new high school, which was really politically problematic. People really don't like when a city cuts down trees, especially in an urban area. And what they usually do when they cut down the trees is they chip them up and they turn them into mulch, and all of the carbon that's sequestered in the cellulose and the fibers of the trees gets released back into the atmosphere in a few years. What we instead did was say, well, could we use parts of these trees instead in a structural way? Of course, trees are used for structures all the time, but traditionally the nodes or the forks are not used because they're so irregular. It's so hard to think about how they might be used. But in our work, we developed a computational method based on the idea of constraints. So we said, if we have this inventory of available tree forks, what kinds of structures can we make with them? And it's a different type of process than a normal architectural design process where we start with a blank page. Here we start with an inventory and say, what can we do with it? And we developed a computational method to optimally match our inventory to a target structure and then morph the structure in response to the available material. We also took advantage of advances in automated fabrication again, where once we had the structural design that we liked, we were able to machine and process all of the tree forks that we had in an automated way using robotics. Here we combine a very traditional bandsaw with a very new, large 6-axis robotic arm who is able to debark the tree fork in an efficient way with a few cuts, where all the tool pathing is automated and based on the design process. And what's nice about this, even though it's kind of a very technology forward approach, the assembly is incredibly straightforward. We basically created a kit of parts for ourselves where all of the geometry is driven by these existing tree forks, and the assembly is completely straightforward because we don't need to figure out any of the angles. It's all already encoded in the joints. So it's like assembling something made out of Lego parts, except the Legos come from the natural geometry of the trees rather than a pre-established standard set. We're also thinking more generally and in sort of a broader sense about how to do material reuse in structural systems. This is a tool that we use in our teaching for teaching architects about structural systems and carbon mitigation. Here, this is a tool that we built where we show if we had a constrained inventory of linear elements, for example, that were waste from a previous construction project or reclaimed from a building being demolished, how do we optimally allocate them to a target structure? This uses the exact same underlying computational method as the tree forks, but just illustrates this in a more generalized way. And this is an area where we're excited to continue to do a lot of work. But what I think is important about this is it shows that reusing material doesn't need to be a bespoke kind of impractical thing. We can really start to scale this up through modern computational techniques. So with that, I'll conclude with some final remarks. I think performance must play a role in the design of buildings and infrastructure in architecture and in engineering. And we can do this if we kind of combine our understanding of design, geometry, and performance driven by recent advances in computation so that we can more naturally link systematic performance-driven design, the human creativity that is intrinsic and central and critical to that process so that we create relevant work for humanity, and we do so in a way that is economical and affordable to construct. Thank you very much.
Thank you, Caitlin. That was a really inspiring talk. I really enjoyed it. We've had some questions come in, if you're okay for me to kick off and ask some of them.
Sure.
Okay, so the first one is relating to the tree forks that you've just been going over. They've just asking if you can expand a little bit on that, and will the forks break down over time, and how long will the buildings last for?
Yeah. Well, we know a lot about timber as a construction material because we've been using it for thousands of years for buildings and also for structures that undergo a lot of stress, like boats. So we know that trees create really amazing materials that we know how to use. The tree forks are the same material, so there's nothing kind of fundamentally problematic about the forks themselves. And what I think is really amazing is that their internal fiber structure is this very complex three-dimensional network of interwoven elements that is incredibly strong. On a tree, every branch is a cantilever, which was one of the hardest things to engineer. And it's the internal fiber structure that makes the moment connection, the rigid connection of that cantilever work. So they're incredibly, they have incredible potential as structural elements. I always say that it's not something that we could never manufacture something as complex as the internal fiber structure of a tree fork today with, for example, what we can do with 3D printing. We're very far away from that. All of the effects of anisotropy and complex the sort of composite nature of the material are handled through the organic nature of tree growth and the performance of the tree. Of course, there are always considerations with timber that as humans we've figured out how to do that very well with types of materials we've already used. You have to protect it from moisture. Ideally, you don't want to expose the end grain. Certain species have more natural resistance to rot and pests than others. So all of that still comes into play, and I think all of that is interesting to consider, to think about. But fundamentally, the prospect of this, I think, is really exciting, and there's a lot of potential there.
No, thank you. It is really exciting. Okay, so we've had another question saying, how do you come up with your ideas? Do you look for everything, whether it has potential for building and the design application?
Yeah, that's an interesting question. In research, a lot of times we have this model of either the hammer or the nail. So some people work on hammers, like methods. I'm making a really great hammer, and my hammer can do lots of different things. And other people have a nail. I have this problem I'm trying to solve, and I'm looking for hammers. I think I'm more of a nail person. So the problem that I'm really interested in is how do we improve the built environment through design and construction, and then I am kind of fascinated by all of these new hammers that I keep seeing emerging, or the potential for new hammers that I see in other technologies. I think the field that I am working in is one that has been less receptive to innovation for the past few decades. So there's a lot of untapped potential where when I look to neighboring fields, when I look to what my colleagues are doing in aerospace engineering or in the automotive sector, or more generally in computer graphics or generalist machine learning, I see amazing things that they're developing that aren't quite ready to be adapted to the building sector, but where I see a lot of potential. So I take a lot of inspiration from interdisciplinary exchange and trying to understand what my colleagues are working on. But then on the other side, I think there's so much that we can learn from just from history and from artists and from people who are thinking outside the box or thinking differently than we think today. And I think that's another problem with the construction sector, is that we've really kind of overly constrained our field where we see things in a very, very narrow way today. But if we look even 100 years ago at how people were building buildings, it was completely different. And there are a lot of really great ideas that maybe didn't make it then because we didn't have the right technology, but that are worth revisiting. So I think that's another, for me, a really important source of inspiration.
Definitely, thank you. And we've had another question in to say that you touched on educating students and how it differs between disciplinaries, and I wonder if you've seen students being more globally aware of impact of materials and desire to reduce impact on the environment.
Yeah, I mean, our students are at the forefront of all of this with climate change and in terms of trying to play an active role in fighting it. And I think they're really leading the charge here. They're super interested in this topic, and they're super interested in creative solutions to it. The materials question is one that I think a lot of awareness has been raised very recently, maybe in the past few years. And so, yeah, we do use it in our teaching. All of our students in both architecture and structural engineering are learning about embodied energy and embodied carbon, how to calculate it, how to understand it, how to try to reduce it. So I think that's really important. Because this is such a new area of interest, there's also there's a lot of misinformation and a lot of confusion on some of these topics. So I think we continue to work on how to understand these issues as best we can ourselves, and then how to communicate them as clearly as we can to students and the public. And I think that's super important as we go forward, that we're very clear on what actually matters and how we can do this in a responsible way.
Okay, that's great. Thank you. Another question just popped in. Have any of the multiple objective designs been built?
Yeah, that's a great question. We have worked with a number of architecture firms and engineering firms in practice who do use some of these techniques, and we help them with some of the tools that we're working on. I think the multi-objective optimization one is especially interesting to people in practice because it touches so directly to problems they see every day, where my client wants this, but I know I also need to do this, or the building code says this, but I also have a budget, or there are always these scenarios. So yeah, I think we are definitely starting to see examples where, for example, I'm trying to build. I want the overall profile of my tower to have this shape, and we've sold the client this beautiful shape, but now we need to fit in all of these hotel rooms that all have very specific geometric rules, or they all need to be the same, but I want the shape to look like this. Those are the types of problems that I think are on the ground, like are already applying these ideas to. The ones that are more based on simulation, I think, are the ones I'm more interested in, where, again, we take things that used to be the domain of these very kind of isolated consultants and start to integrate them into synthetic and design tools. And that, I think, we're a little further away from getting that into, because we still need to solve some of the problems with interoperability and simulation speed. But I think that is really where I see this going in the future. Hopefully we'll see a lot more of this kind of thinking being used by engineers and architects.
Okay, great. It's so interesting. So we've got another question here. Given the fact that the deconstruction is carbon intense when it comes to urban regeneration, is it better to make older buildings more efficient or in the long term knock them down and build new and low carbon processes and materials?
Yeah, that's a $1 trillion question. That's a really great question. And I know that people want the answer just straight away. You have to run the numbers. Unfortunately, understanding carbon emissions, especially related to materials, is, first of all, no one has a lot of intuition for it yet because we just have only started to benchmark this recently. But it also is really, really varied. Some of my colleagues have been working on databases of carbon associated with various construction materials and various buildings, both existing and new construction. And one of the main takeaways that I've seen is that it varies tremendously, right? The embodied carbon in a structure can vary from 50 kilograms per square meter to 1,000 kilograms per square meter. And it's pretty well distributed through that range. So depending on what the replacement would look like, it may be more carbon efficient to take down or demolish an existing building and replace it, especially if it's very poor performing operationally. So if it's in an intense climate, a heating or cooling dominated climate with high operational energy needs, and it's hard to retrofit, it may be worth it in the global carbon sense to replace it. But I think as an industry, we should figure out how to do retrofits economically so that we can at least reuse the structural systems even of existing buildings. Because most of the carbon emissions embodied in construction materials is the structural system, and structural systems are usually designed to last infinitely if we take care of them. So my personal preference would be try to find a way to at least reuse the structure, and upgrade the building envelope and the heating and ventilation and air conditioning system so that it is minimal in terms of its energy consumption. And I think that it's also, in addition to carbon emissions, just in terms of limited resources and changing our mindset in terms of how we take care of these precious resources we have. Building materials are precious resources. We don't have them in infinite supply. We should be really, really careful on every single project, thinking about what we can still reuse. But the final answer, I think, still comes down to quantify it, because it's very hard to know ahead of time. And I'm hoping that we'll see more tools going forward to help designers quantify these kinds of things for these types of questions in a way that doesn't require extreme amounts of time or expertise. I think that's very important.
Okay, thank you. And I've got one final question, which is there are many alternatives to concrete being developed, for example, hempcrete or timbercrete. As they are relatively new, how do we know how durable these will be in the long term? For example, mycelium breakdown over time as it is vegetable based. Would using recycled plastics eventually add to the microplastics pollution problem?
Yeah, these are all also really, really great questions and things to think about. When we see new materials, one thing that's important is to understand their properties and what their potential is. Things like hempcrete and timber reinforced concrete, I think, are very interesting, but most of them are not necessarily immediately competitive with traditional concrete because they have different strength profiles and are being proposed to be used in different ways. Personally, I'm not fully against concrete. I think it's an important material that is going to be central to meeting, for example, the UN Sustainable Development Goals of bringing millions or billions of people out of poverty who need housing. We don't really have a way to do that without concrete, but we have to be very, very careful about how we use it. So, for example, I don't think we should be using concrete in non-structural functions like partition walls. We should absolutely explore things like hempcrete or even just fully bio-based materials, especially for parts of a building that need to be replaced more frequently. It makes a lot of sense to look at things that are bio-based or that break down quickly. For parts of the building that need to be durable and ideally last for hundreds of years, yes, we should be careful and try to use materials and protect them in such a way that they can do that. I think that the advances that people are making to concrete are very important, and I continue to keep up with all of them. But I would just caution that one of the easiest things we can do now is just use less of it. Even if we're not using a fancy new concrete that somebody is still developing, just use less. It's in any concrete structure, it's relatively easy to reduce the amount of concrete by half by just paying attention to where we're using it, not using it in non-structural applications, and paying attention to shape. And these are technologies that we already have used in the past. So it's just, again, it's a change of mindset that I think is very important. So I think we should continue to explore all future sustainable materials. We should understand their durability, and we should just use only what we really need to use, especially for carbon intensive materials.
Okay, great. I think that's the end of the questions now. So once again, thank you so much, Caitlin. It's been such a privilege having you join us here today in Wales and opening up our eyes on the construction industry.
Thank you so much. It was wonderful to be here too.
Okay, and thank you to everyone who has attended today's session. The next session will take place on Wednesday, the 16th of March, with Ritu Ramin, who will discuss empowering women in STEM and advocating for diversity. So thanks again.